So, uh, we're pleased to have Hari here. So, Dr. Harikumar Kandath received the PhD degree in aerospace engineering from IIT Bangalore in 2015. So, he has held research positions at NTU in Singapore, SUTD in Singapore, and at the University of Mako in China. He's working as an assistant professor with the Robotics Research Center in IIIT Hyderabad, and he's been there since March 2020. His research interests are in the applications of robotics, my bad, of control theory to unmanned systems, UAV design, and flight dynamics. So, Hari, over to you. So, just one bit, are you okay with people asking questions like in the middle of the talk, or would you prefer that they wait till the end?
Sure. That they can stop. I think that would be better. I think.
Okay. Yeah. So, folks, if you want to ask something, just raise your hand, or if you want, you can just type it in the chat box, and one of us can, just bring it to Hari's attention, and we can take it there. All right, Hari. So, yeah.
Okay, sure. So this talk I'll mention about the two vehicles built by our students at our lab at IIIT. 1 minute, just I'll go. Okay, so the contents will be I'll talk about two unconventional the vehicles. So the way I say unconventional means most of the time when we say UAV, it comes like multi-rotor, hexacopter, quadrotor, or the fixed wing category which comes in our mind. So in this scenario, we are trying to build slightly unconventional in that sense when compared to the normal vehicle. That one is a combination of the fixed wing and flapping wing in a single vehicle. So we call it as a hybrid fixed and flapping wing UAV. The second vehicle, what I'm going to say is about the spinning quadrotor, and it will have additional mechanism to enhance the thrust. Okay, so we'll discuss about these two things, and I will use for the design purpose or the understanding, I'll use very basic equations. I'll just show a few things, and after that I'll go to experimental results. I'll show some videos and the corresponding experimental data what we have got. Okay, so feel free to stop for any clarification. So when we compare, I think suppose people who are not from the aerospace background, I would the differences comes here is that for fixed wing UAV compared to flapping UAV, you can fly faster, you can fly at high altitude and have extended range. But problem is that you cannot fly slow. Slow means typically, let's say I want to fly at 4 meters per second. Practically, most of the vehicles will not, a fixed wing cannot do. I need to have typically at least 8 to 10 meters per second. Most of the UAVs what we fly. So what is the problem in that case? The problem is that I cannot like maneuver easily. Like you cannot fly slow means you're not able to maneuver easily. So avoiding trees and buildings would be difficult. So you are forced to fly at a very high altitude typically. And typically the wings will get stalled at what we say angle of attack. I'll show the diagram of angle of attack later, like what you mean by that, at 15 to 28 degrees. When we go to flapping UAV, it cannot fly faster when compared to fixed wing. It has to fly at low altitude, but the moment you try to climb a very high altitude, most of the battery will be drained, and it has a low range, right? But the advantage is that it can fly slow. Okay, so when you can fly slow, you can have a smaller minimum turn radius constraint. So you have a what you call the very good maneuverability when compared to fixed wing. Okay, so and even if the wings will not stall, you can fly angle of attack exceeding 30 degrees for flapping wing. So the idea is that suppose we make these two things in a single vehicle. So eventually what we are trying to do eventually is that let's say if we are trying to do a simple surveillance operation. Let's say the point of surveillance is far, let's say 10 kilometers away from here. So flying a quadrotor till that point will, let's say, consume a lot of energy, right? So instead of that, what we do, we want to fly faster, we use a fixed wing. And once you see something of point of interest, let's say you want to go down to view it in a better way, something like that. So what we do is we try to switch to flapping mode and we have to come down. That is the idea. So we have just started these experiments and we are able to at least stabilize the vehicle, single vehicle to fly in both modes. That's what you achieve. No, we are not flown extensively this one. One difficulty is that you need expert pilot. Unlike quadrotor to fly these vehicles, we need expert pilots to fly unless you fully automate it. Again, fully automating it, again modeling and you need to have a very good model and a feedback control. So that again takes some time and effort. So with the basic design equations and principles, I will just convey here in this talk. So for any flight, actually, these two are the very common equations what we use, right? The lift, the force should balance my weight. And since you are moving in a medium, the medium will oppose you. So I should have some thrust force to balance the drag. Okay. So in the case of fixed wing, these are like well-known equations. So lift is proportional to the square of the airspeed, the density of the medium, the wing area, and what you call coefficient of lift. similarly, drag also you can quantify in a similar way, where coefficient of lift is replaced by the coefficient of drag. So this coefficient of lift and coefficient of drag varies with as a function of angle of attack and Reynolds number. Also, when you're talking very high speeds, the Mach number also affects. But since we are talking about the small UAVs, we are not considering the Mach number effect. Okay. So normally, if you want to analyze like a few airfoils and wings, typically the software which is can be commonly used is XFLR. So XFLR is the base called Xfoil. This is the dedicated software for what you call low Reynolds number flight. Typically, what if I like 20, 30 meters per second, or most of the flight what we do for normal UAVs comes under this regime. You can use the software. It's pretty easy to use. You don't have to have in-depth knowledge of CFD to use this one, and you can quantify all these forces using that one. Okay, so lift it will quantify reasonably, almost like some 80% accuracy. Drag, one problem with drag is that it will try to underestimate the drag. Okay, so normally what you do is that you whatever lift it predicts, in practice you may achieve some 80% of that thing. And drag is one problem that the fuselage or the body of the aircraft it will not consider. So that's also we need to have corrections for our additional corrections you have to do for that. And also the other problem is that the screen friction, because the material you might be using, right, the drag will change based on that. So the material property we cannot enter. So it will assume a smooth surface and compute the drag. Okay. So typically most of the drag is estimated from actual what you call as like internal testing. So only whatever software we use, most of them will not able to exactly capture the drag. Okay? So this is the one common way you can analyze different wings and airfoils and come up with a efficient design. Okay. So normally what we look at is for endurance, we should have a very good L raised to 1.5 by D ratio. So that's the one thing. And for having a good range, we look into the L by D ratio. So these are the very two common metric what we follow for designing a fixed wing. And so this is the definition of angle of attack. This is taken from the Anderson book actually. So this is your free stream air which is coming, and this is called airfoil. You cut from side, right, from wing, right? You see from side, you cut it, you can see this cross section. This is called airfoil, right? So this is called chord line. So this is the what is called the leading edge and trailing edge. You just connect using line. This is the chord line. Okay. So what and the angle which makes with the free stream air is called angle of attack. So this as angle of attack changes, the forces also will change. Okay. So this is the resulting aerodynamic force, and which is parallel to the your free stream speed. If you resolve it, it's called drag. Its perpendicular one is called lift. Okay. So this is the basic idea. So when coming to flapping flight, it is since you are also flapping. In this case, so your relation becomes slightly more complex. So unlike fixed wing, you have to keep in mind that flapping wing generates both thrust, forward thrust, and lift using only flapping. Right? We don't have any additional thrust generating propellers for that. Okay. So for the flapping flight, what happens? This amount of thrust generator is quadratically related to your flapping frequency. Okay. And your wing area. This is called your stroke angle. Okay, that means the angle you can measure like in one stroke going up and down, how much angle you are covering. Okay, this is the question which relates that to. And if you see now, the question is that what kind of flapping like frequency I need. Okay, so for a given weight, so I think people have analyzed mainly from the birds. Okay, birds they have analyzed like what kind of flapping frequency and what kind of weight it has. So this 6 is mainly derived from the analyzing the behavior of birds. Okay. So this is the mass, and this is the gravity, and B is the wingspan, S is the what is called the wing area, and rho is the density of the medium. Okay. So in this case, what happens is that this efficiency factor eta, what you call, is 1 for the birds. Okay. But when we try to build our own vehicle, normally what happens is that our like wings are not as efficient as the birds for different reasons. So in that case, what happens is that your eta, whatever flapping wing model they have analyzed, eta can go from a percentage like 1.52 or 1.7 starting to till 4 it can go. Okay, so that means at least 1.5 or times higher frequency is needed. Suppose you are going to build a vehicle for carrying the same weight as similar to a bird. Okay, so that is the idea here. Okay, so again when you talk about this lift and drag, same equations will follow for the lift and drag. Again, we can use allows to XFLR. We have one more software called Pitera. Pitera is a software you can use to get this lift and drag. Okay, so one thing you have to keep in mind that lift and drag is a function of time here, as the since you are flapping, based on your flapping one cycle. I'll show some diagrams. This will change. What is called the amount of lift and drag generated as a function of time. It will change. Okay. So one approach is that you can average. So this the what is called the averaging of the input forces, right? So this comes from the basic idea is that your vehicle has natural frequency. Let's say you consider the motion called pitching motion. That is the motion along what is called XZ plane. Okay. So pitching motion is same thing. Suppose you are not getting the idea. Suppose you can simply assume that suppose you are sitting in a flight, right? So when there's a gust, you start moving up and down. You start oscillating up and down, right? So that is typically the motion along XZ axis. That means you have a rotation along y-axis. So your XZ things will change, right? So that is basically the what is called the pitching motion, like what are thing you are feeling. Okay. So basically you'll have you can approximate it by a couple of second order system, and you will have some natural frequency for that. Okay, that means if I give some input to the step input, let's say in your elevator, like what kind of response you get from that you can analyze actually. Okay. Now what says that the flapping frequency is much higher, maybe 5 times or 10 times higher than the natural frequency, then this averaging perfectly works. That means you can consider it's like a fixed wing UAV, and all the forces you average and take it. Okay. So that's the thing. But the problem comes when you start flapping at very low frequency. Suppose your natural frequency is closer to the flapping frequency, then you have to use the actual time varying equations. Okay. So when you talk about the dynamic stability, in the first case, when you're considering it as a fixed wing, you can use the normal linearized model, state space model, and you can analyze the eigenvalues of your A matrix to find out the stability and instability. So that normally what happens that with respect to your CG location, right? Your CG location, if you keep moving backward of the aircraft, at a certain point of time, you can get an unstable vehicle. Okay. So that's what you call static margin in fixed wing vehicle. Okay. So, but in the case of flapping, as we mentioned before, if the frequency is flapping is higher when compared to natural dynamics, you can consider as a fixed wing by averaging forces. Okay. So the same analysis will follow. But in the second case, if your flapping frequency is comparable to the natural dynamics, then you have to use the theory of the time varying system, what you called Floquet theory. So in Floquet theory, again, you can analyze the stability. Okay. So these are the two tools which we commonly use for analyzing the stability. Okay. So this one example, this is using Pitera software what we have obtained. This is for wingspan 1.4 meter, and we have used typical NACA flat plate airfoil. The flapping at 3.2 hertz, and this is the chord length, and this is 10 degree angle of attack, and stroke angle is 52 degree. Okay. So this is the after averaging we are getting like this means close to like 480 grams of lift, right? You multiply by 9.8, you get close to if you convert it to grams, right? It's close to 100 conversion, so close to 480, 490 grams we'll get. And similarly, this is the drag, and this is the pitching moment. Okay. So now, if you see the plot, actually, right, the plot is interesting. So this is what we are saying. This is the average value what you have shown. So, but you see that your lift is there, which is shown here. This varies as a function of time. Again, this is the drag. Okay, this is the drag which is shown as a function of time. Okay, so when you talk about when you say drag, right, the drag is this is the net force. That means the difference between thrust and drag what we are showing here. Okay. So unlike the conventional fixed wing where we have separate mechanism of thrust, here you have only one mechanism. So this is the difference between those two, drag means. Okay, that part has to be clear here. So similarly, you see this is again the pitching moment, because your vehicle is symmetric about the other two axes. You don't have any rolling or yawing moment, but you'll have CC pitching moment varying as a function of time. Okay. So we try to build one. So this is the CAD model. So I think this tail is a conventional tail what you use to elevator and rudder. And this powertrain model we tried to first what we tried that we tried to separate, like that means this powertrain will actuate only this is a BLDC motor. This will actuate only the wings, so fly like a flapping mode. Second time we modified this one when also we added propeller. So in that case, both propeller will generate thrust, also the wings will flap generate additional thrust. Okay. But in that case, there was no independent control. That means whatever there's only one control, which one actuation which controls both forward propeller and the wing motion. In third case, what we did is we tried to separate these two. So we added one more motor so that we separated this forward this propeller and the wings. So we actually flight tested all the 3 configurations. So this is the first one. What I was saying is that the first one, rest of things are same, only the front portion is different here. What you have seen here, rest of things are same, only this portion is different. We have tried 2 versions. So this is the first version where you can only flap, right? This part is connected to the wing for flapping. In the second case, this is different case where you use slightly bigger motor, and we added a propeller to it. So in this case, there's only one motor which actuates both propeller and the flapping mechanism. Okay. So this is the flight test we have done. So if you see here, go back here from the Pretera predicted, right, almost close to like 480 grams of the lift. But if you see where we are able to carry till 420 grams. So the first one, which is the default, means the one which does 9 propeller. So the motor is smaller one. So this motor is bigger one in case. That's why the weight is slightly higher. Okay. So extended range means the one which is having a propeller. Okay. So Pretera was reasonably okay. It predicted up to close to 480, 490 grams of lift, but we are able to fly actually with only flapping close to 400 grams. So almost you can say maybe 80%, right? 80% accuracy will be there. Okay. And and this endurance range, we could not fly this for entire duration, but for the few, maybe 30 seconds, 40 seconds we flew, and we tried to measure this, what is the power drain from the battery. Based on that, we were able to estimate the endurance and range. So the default profile, right, what that means, the only flapping is there, can fly till 2.8 kilometer with 9 minutes, and when we add a propeller, we will be able to fly 17 minutes and close to almost like 3 to 8, more than 2 times, right? You're getting endurance much higher than this one. Also, we can fly at much higher speed. Okay. So this is the thing, what you have tried, and maybe I'll show one video for this one. I think you guys see my screen, right? Video.
Yes, sir. We can see.
Okay. So this is the default one without the propeller. This is the one with the additional propeller we have added. So this one, you can one problem that it has higher pitching moment because this propeller thrust was slightly off from CG. It was getting slightly additional pitching moment. So in the third case, we separated both. Now we have 2 separate controls. In this flight, I think we have 2 separate controls. So in this case, it was easy for us to climb because it has higher power. It was easy for us to climb and fly. So now you are trying to fly this for a longer distance, but the pilot is not expert. So that is the one problem. And so this is the first regarding this hybrid vehicle, what I'm talking about. The second one is called spinning vehicle. So I'll just show this video, then it will be much more clear. So second vehicle, what are we talking about? This is spinning vehicle. So in this case, so this vehicle, what we saw just now, yes. So this vehicle, what we saw, which it had a big propeller in the bottom. So the idea is that, for example, when you want to do inspection of, let's say, a tall industrial tower kind of thing, most of the time what we do is we spend a lot of energy by climbing. So the thing is that now the question is that when we are doing this climbing, can we also rotate? So nowadays we get what is called the programmable speed controller, where you can change the direction of the motor anytime. Okay, so you can naturally make all the 4 motors rotate in the same direction, and you can induce what's called yawing moment, and you can rotate, and then you can climb. So when you do this thing, can use additional surfaces which can be used to generate thrust. Okay, so that's the first configuration what you saw is where we keep a big propeller in the bottom and then we are flying that one. This is the other configuration what you tested. This is like is similar to wings. That means that instead of the big propeller, we are reducing it a very small portion, and we are keeping on the towards the edge. Okay. So why are keeping the edge means when this rotating, we get the edge, we get the higher tangential velocity. So we get slightly better what's called higher Reynolds number, so that the efficiency will increase. So that's the idea here. So in this case, the design, the key parameter what you have to look is the high lift to drag ratio. Okay, because the moment you have a high drag, the problem is that you are naturally trying to spin at higher rate, but that drag will oppose that. Okay, so but stability point of view, that drag is good. Suppose you are trying to spin at too higher rate, then what is going to happen is that if you exactly look into the flight dynamic equations, there's a coupling between your roll rate, pitch rate, and your rate. If you are spinning at a very high rate, that becomes prominent, and that might create a problem. Okay, that coupling effects might. Suppose your PID, whatever you do normally, it is not designed for that high spinning rate, but the spin rate is more. You are technically you're able to generate more lift. Okay. So that's also you'll get higher upward force to fly. So that's the idea here. And also this has additional advantage that we are still working on that part. That theoretically that if one of the motor fails, it has some that will able to stabilize this vehicle by using this angular moment of this rotating parts. Okay, so that's additional thing what we are looking into for this kind of vehicle. Okay. So in this one, basically, what we are trying while designing, we tried multiple airfoils. Unlike previous case, not flat wide, we tried multiple airfoils, and we were trying to choose the one which is having a good sail and good sail by CD ratio. So this is the one of the things. And other thing you see that based on your length, right, based on your arm length, there will be a Reynolds number range which you can attain, and also the maximum spin rate you can achieve for your vehicle, right, based on the basic vehicle configuration. Suppose you don't want to put additional controller, your basic PID, there's a limitation of the upper angular rate which you can do stable flight. Okay, so based on that, you can get the Reynolds number range, and you can try to optimize your airfoil combination, wing surface combination for that particular this thing. Okay, so that's how this vehicle was designed. I'll show just some results from the data what we got. Okay, so this is the case. We tried two things. One is the 4-wing and 2-wing, but that you have seen before. And 4-wing, additionally, we are just slightly like canted the motor like 10 degrees, so that you'll get additional yawing moment, so you can spin faster. Okay, so you can see that the total vehicle weight was 960. This is just the RPM of the PWM value of the speed control. You can neglect this one, and you can see that this motor thrust based on this value, right? This is higher means, see, this is 148 1809. So this is higher here means you are generating more thrust from the motor. But for this one, it is giving only 758 from the motor. Okay, so close to like 200 and something grams we were able to get from the wings what we have mounted. Okay, so almost like a 22% of the total weight we are able to generate using this rotating thing. Okay, so since you have used 4 wings per wing, it is 53. You can get this one. Okay, similarly for the 2-wing case also, you can see that you are getting additional lift of like 147. So we are getting additional lift per wing as 3.4 here. Okay, so that's what we have seen here. I think I have one video also for this one, for just a preliminary testing. So this is for collecting data for between two different. First, without spinning, as in case we are spinning it, and so we were able to spin. I think up to like 10 radian per second kind of thing. We were able to spin this one. So what you have seen is that one is for getting achieving high speed. High speed, you need to default the pixel control cannot handle. You need a custom controller. So that we are designing, so that we will be able to spin this for a very high RPM. And second thing is that can we use this one for as a one of the motor fails, any fault tolerant capability can we use? So that is the additional thing like what we are trying for this vehicle. This is very specific case is up when you want to climb too high. That's where you can use this mechanism to generate additional force. Okay. So I think these are things I have to share. So mainly acknowledgements to my students, Naib, Srinath, Aniket, Ritvik, and Prashant. So I think I can open for discussion. I think.
Hey, thank you, Hari. So, guys, we have quite a bit of time for questions. Anybody? Yeah, go ahead, Aman.
Yes, sir. I'm a bit unclear on the applications of these UAVs. Like, how are they better than simple quadrotors?
So when compared to quadrotor, right? Quadrotor, one option is suppose you are you are going for a surveillance operation. One is that your quadrotor is not operationally signed. It makes a lot of noise because it has multiple 4 or 6 based on quarter hex. A lot of sound is coming. And second thing, compared to fixed wing, you cannot fly faster and far distance. Like fixed wing, you can fly very far, right? So let's say you want to fly very fast and very far. Your quadrotor, I think the cost become very, very high. The kind of propellers and mechanism you have to use, that cost become very, very high, and it makes a lot of noise. Okay, so typically for any surveillance applications, you think, let's say I want to fly far, and after that you want to go slow based on the region which you want to operate. That's what you are trying to do. That whether the combination of fixed wing and flapping can be used, so you can go slow. Yes. But the more thing is we are considering also the thing as a research point of view. Because once you convert into one vehicle to another vehicle, right, there's a transition between these two vehicles, and the flight dynamics properties what you get for these two vehicles are slightly different. So all of the things are like interesting research problem also. So that's also the other aspect.
Okay.
Any other questions? Let's see. Okay, so let me ask you a question, Hari. So you used a commercial tool, right? I think aerodynamic forces and moments.
Yes.
Right. So just out of curiosity, how good was the match that you observed on the flight?
Yes. So this what we have this predicted this close to 4.9, very close to 480 grams. It predicted by the software, and we are able to carry close to 400 grams fly.
Okay.
Yes.
But did you check where where the predictions matched well, where they did not? Because one of the things that we had observed, of course, was we don't know what's kind of going on under the hood with those tools.
Yes.
But in general, writing out precise models is generally quite tough for flapping wings.
Yes.
Yeah. So very often you end up having to make assumptions. Of course, the good thing about larger wings is because you're still not going at extremely high extremely fast flapping cycles, you'll probably get a good match any which ways.
Yes.
Okay.
That's correct. As you go with wingspan small and high, very high frequency, problem is still more. Even this is seen for fixed wing. So I have previously flown fixed wing of like a 150 mm wingspan, a very small one. So in that case, what you are seeing is when we did the internal testing, what you observed was the propeller effects was very significant.
Yeah.
So you have to include the lift drag and moment, even the side force, the effect of propeller was very significant. So we cannot neglect that. So internally is the only option in that case.
Yeah, that's true. Yeah, with the prop especially, yeah. Which I was going to ask you, because the problem with the prop is, it's not exactly right. You can write like some cycle average thrust and moment and torque from the prop, but it's not strictly that. It's actually cyclic.
Yes.
So which is, I was like, if you've got a flapping wing in the wake of a prop, I was very curious. I was like, what kind of profiles did you see in the dynamics?
Actually, I have some flight data. Maybe I can share you that one.
Yeah.
But most of them we got since we had a bigger wingspan. Most of them we got more like periodic pattern itself.
Okay, pure periodic. Okay.
So more periodic pattern only we got actually.
Okay. Yeah. And just wanted to know your thoughts on this, because now you've actually flown these things, right?
Yes.
So with standard fixed wing planes, the idea of stability is clear. You want to be at an equilibrium condition.
Yes.
For a flapping flight, the expectation is that you will probably want to do a pure periodic motion.
Yes.
But quite frankly, even if you have like a period 2 kind of oscillation, where you have one dominant frequency, not dominant, but let's say you have two frequencies coupled.
Yes.
It doesn't look like it's such a bad deal, right?
Yes, yes.
Because as long as all the states stay bounded, you're able to fly a prescribed flight path with guaranteed errors. It shouldn't matter. So, just out of curiosity, what was your? I mean, so when you designed control laws for these vehicles, what kind of error metrics did you use? I mean, were you okay accepting like the periodic variations? Did you like just
No. Still, it is open loop. Whatever you are saying is open loop with only pilot input. There is no model-based control, feedback control here. So that's why we are finding difficult to fly for longer duration. Pilot, unless the pilot is expert, after a few seconds we have to land. The pilot has no clue how to fly for long distance. So we are just identifying the model now as of now for the control design. So that process is ongoing. But what you have done is that this accelerometer data, when we did the frequency analysis, dominant one was near to the flapping frequency what we have designed it for, what the dominant frequency. And we had also like subbands were there, subbands were there in that also. But this was the dominant what we saw.
Yeah, that is what you would expect to see.
Yes.
But I think the idea is like, for example, in a typical fixed wing airplane,
Yes.
because your baseline is in equilibrium, we don't accept limit cycles usually. Although
Yes.
like with some combat planes, they'll still say, if you have an unstable fugoid, it's okay, we'll let it through.
Yes.
I mean, at the time of certification.
Yes.
But here, your baseline anyways is periodic. It's not an equilibrium any which ways.
Correct.
So, one of the things that I've always wondered, I mean, we've of course got things flying, that's a different story.
Yes.
But like, what would be a nice principled way be to feedback an error signal to the control law? I mean, like, do you just cycle average it, but then you have multiple cycles? So anyways, but yeah, that's something I think maybe we can talk about that independently as well.
Yes.
Okay.
Sure.
There's a question. There's actually a comment and a question, I think. So this is from Prashant Devarahatti. He's saying he loves your work on propelling the aerial vehicles with unconventional models. As the research is still in evolving mode. So I suppose the question is this. So what if the main research domain is to reduce the sound? So I think he's talking about the acoustic signature.
Yes.
What's your opinion on overspeeding the motors above 20 kilohertz? So it's not in the human audible range. I think that's an extremely high RPM.
Because then you then in that case your propeller size should be very, very small. So whether you get any actual benefit out of it, that
you're
not able to spin very high dimension propeller with very high. That's not possible. So
I'm just wondering, like, what happens if your propeller size shrinks to that extent? Your Reynolds, I don't know what the Reynolds number will look like in those cases, because I'm assuming that when you spin them, you'll still try and hold a Stowell number on the span of the prop.
Yes.
Yeah, I don't know what the Reynolds number will look like. Yeah, you're doing omega C, that's holding. Yeah, that should be bizarre actually. Okay. Yeah, it's just so Prashant, I suppose the answer is principally it sounds like a cool idea. The issue is when you go to those higher RPMs, the propellers shrink a lot, and that may or may not be great from a purely flight dynamic perspective. But I think it's a bit of an open problem. I don't think I've seen any frequencies going that far up. With insects, we see them going into hundreds of hertz. I'm sorry, but not like 20,000.
Insects, but they have different.
Yeah.
They have this biological engine.
Yeah, absolutely.
I was discussing with one of my colleagues. He was saying he had an interesting observation for this. He told, if you build a mechanical engine, you'll get a mechanical efficiency. That's only possible. Suppose you want to fly like a bird, you need a biological engine. Then only you eventually you'll be able to achieve that. Otherwise, you'll get a mechanical efficiency only for all these devices.
Yeah, that's true. And I think the other interesting thing that still remains is like the base motion where flapping starts is still the spinning motor.
Yes. In
the human body, the base motion is actually translational. It's not rotational at all.
Correct.
And so yeah, that I mean, I don't know how to solve that problem at a mechanical level, but I just wonder, like, if you go from rotations which seem very efficient on the face of it to pure translation, does it actually gain any efficiency across the entire structure? But okay, good. Yeah, guys, any other question? So otherwise, I'm going to keep making random comments of this sort, and it's not going to be in anybody's
interest.
I have
a quick question.
Yes. Thank you. Chalo, good.
Hey, Hari. Yeah, great work. I just wanted to understand on the control side, like because modeling these is what really hard is what I'm gathering from Aditya and like your conversations. So have you looked at any kind of like learning based methods like RL approaches for this?
Not, we have not reached that stage. We are still identifying this aerodynamic questions from the flight data. That's what going now. So the problem comes is with RL. The first phase I'll tell you, because I think Aditya also knows we have this inner loop and outer loop, right? In normal, what happens? So even if you see RL thing, even if you see take quadrotor, most of the people what they're trying is outer loop control. They don't directly the angular right to the motor. That control still people prefer to have the PID. Okay, only outer loop control people are modifying and trying navigation, obstacle avoidance, all those things.
Yeah, more at a like waypoint level, you're saying.
So two things. The most difficult come is the uncertainty, because especially if you go to the vehicles more than quadrotor, there are a lot of what is called the dynamic derivatives. That is, the forces and moments change without to change in angular rate. So that's what's called dynamic derivatives. Estimating that is not a straightforward thing. Even mental also we cannot get it. So that you have to estimate through system identification through first principle modeling. We have to identify those parameters, and also think like what is the confidence you'll get when you fly this, because since your parameters are approximate, what kind of robustness your RL can give, that is also like unclear.
But that's I mean, because the way to model this system is so hard, so that's where RL kind of might be a good place. But then also like to train it, I don't know how will you
correct
come up with all the possible.
that's the thing, because we need a good model to train RL. We cannot fly every time. So once you have a good model, then one question comes is that why can't we go for traditional controller? Which gives when the thing is robustness.
No, but you don't need as good a model for RL like as you would need for controls. But yeah, Aditya has something to say.
No, I'm not so sure of that. Huh? So in fact, 2 points here. The first, the thing that sort of just brought it up with Hari, which is, what error signals do you feed to the control law? Mm-hmm. That same problem also arises with RL. So for instance, if your base motion is periodic,
yes,
it intuitively makes no sense to penalize the amplitude. I mean, or maybe it does, but not at any specific frequency.
Mm-hmm.
Right? So, so that's the challenge, which is like, okay, so do you penalize large amplitudes exclusively? So fine, you can use some non-linear scaling function there. What do you penalize? That's the first problem. Mm-hmm. And second, the other
but here your penalization won't be on basically on the amplitude or the frequency, right? Your penalization will be on attaining that pose. Like ultimately, I want to attain that pose.
No,
so you're picking
that's the problem, right? So in flapping, there is no equilibrium pose. The pose is always periodic because as you flap, you have a system which is like a first or second order system that's periodically excited. So you can't get rid of a sinusoidal kind of a profile, right? So that's the problem.
Basically, it's a stable limit cycle or unstable limit cycle. That is the thing we are asking mostly here.
And the other thing is, let's say you have an unstable limit cycle, right? I mean, depending on what happens with the limit cycle, you may end up with, for example, like toroidal behavior, like we saw, like when we were looking at flapping with reducing frequencies, you actually get a period doubling sort of route to chaos at extremely low frequencies. But the point is, because the amplitudes are all tightly constrained, in practical terms, it just doesn't make any difference whether you have a classic limit cycle or you've undergone multiple rounds of period doubling. So that's one of the challenges. Like, what's your error signal going to be? With fixed wing, it's all black and white, right? You the moment you deviate from equilibrium, it's an error. Period. And the other thing I was going to tell you, I mean, it's also fascinating because if you look at nature, so humans pretty much come with no circuitry to walk, but birds do come with basic circuitry to fly. So it's possible that somewhere over the years, through selection, it may have just been observed that you can't fly without a built-in law. And which possibly over multiple generations of bird species effectively get selected for that model.
Right. So what I know is that this, I don't know, they are seen in this, in the latest aircraft, they use something called the incremental NDA, which is, they told that F-35 they are using. I don't know how far it is there, but it's coming in the reporting in the IIIT control system. This also they reported that one. Which is the different the difference from the what you call the conventional traditional PID what we for a long time. That is the thing they told successfully they are using in the incremental NDA.
That's true. That's true. And actually, the amount of model identification they've done is stupendous. There's this whole book on the F-35. With 2 chapters on control design. It makes for amazing. Like, the amount of modeling that they've done, all the way down to fitting derivatives, is just stupendous. There's no other word for it. But anyways, I really think I need to stop. Okay. I get excited about these things, but
actually, that's long back. That even this adaptive control, when they started in the 80s, that is called MIT rule. They tested first in some aircraft, X-plane or something, and they've flown successfully. But after that, it got crashed and one pilot died because then later they find out that they were not able to stabilize robustly. Performance was very good, but robust stability was not there. So many of things, new things we introduce that always when come to aircraft, that this robust stability always matters a lot with a lot of uncertainty coming into place.
True.
Yeah, RL is very interesting. Especially for time weighing system, how to use RL. That is a very, very challenging, or a lot of things to research in that area.
Right.
Okay, are there any more questions, students?
All right.
Okay.
Okay, then so
Yeah.
Sandeep, should we close then?
Yeah, I think that's good to close now.
Yeah. All right. So thank you very much, Hari, for making this presentation and for making the time. So I think I suppose the students probably were like just completely just fell in love with what you've done. So great, guys. I mean, next time if you have questions, do ask. One thing I should tell you is something one of my teachers told me a long time ago. There's no such thing as a stupid question. There's only a stupid answer. So, by the person that told me this was Naira, who invented L1 adaptive control to deal with that robustness business.
Oh, yeah, okay.
Yeah, so you mentioned robustness, and I thought I should quote Naira here.
Yes.
Anyway, so please, always ask, and hopefully we'll see you guys again next Thursday. Thank you, Hari.
Thank you.
Thanks,
You.
Hari.
You and hopefully we'll connect offline.
Still tell me to email anything is there. This is
Yeah.
still undergoing research. A lot of things to do, and we need also a lot of students like you to get it done. Also, okay.
Thanks, Hari.
All right, thank you.
Thank you.
Bye.
Bye-bye.